Okay, so from now on we are going to discuss the phase diagram. Okay, so this is just a general slide where it is talking about nickel based superalloy that is used at very high temperature, so that we need to replace it with some other metal, so that's what it is given over there. Okay, now see, in the case of phase diagram, so basically it tells you that what is this phase diagram. It is basically a diagram where we represent the phases and represent the phases in terms of this pressure and the temperature, right? Because when we represent it in the pressure and temperature, then this is particularly for a single element phase diagram, or that is called as one component system. One component means single element, like suppose iron, water. Okay, like single component is there. Okay, so for that, basically at different pressure and temperature, what are the phases which is there. So now suppose to understand it, you simply take the case of the liquid, that is the water. So water, we know at room temperature it is liquid, but as we cool down, so it becomes solid, right? And if you heat it, then it becomes vapor. Okay, so the x-axis is the temperature and this is the pressure. Okay, so what is the normal pressure? It is 1 atm, right? So it is given in atm, so 1 atm will be here. So it shows that at lower temperature than this 0 degree centigrade, so we have this solid, and between this 0 to 100, so we have the liquid, and above 100, so we will have the gas, that is the vapor. Okay, fine. Now here it is assumed that the pressure is constant. Now what will happen if the pressure also changes, right? So this is what it is shown, that this curve goes something like this, then it goes like that, and it goes. So in this region, complete region, at this like pressure and temperature, so this will be in solid, and this will be the liquid, and this will be the vapor. Okay, fine. Okay, so you can also understand, see, the boiling point of water, where we are converting from liquid to solid, it is 100 degrees centigrade at 100 at 1 atm, 1 atm, that is the pressure. Now suppose you reduce the pressure, I'm reducing the pressure, going down. So once we are going down, so the temperature at which this liquid becomes vapor, it is decreasing. That means we can boil the liquid at lower temperature. So this is what the meaning of pressure and temperature relation is, that it's not always that water boils at 100 degrees centigrade. Yes, that boils at 100 degrees centigrade, but if we keep the pressure 1 atm, if somehow we can reduce the pressure, then it will boil at certain lower temperature. So that means if you are heating water at high altitude mountain where the pressure is low, so in there basically you are going to consume less fuel. Okay, next. Okay, now we'll understand what is a solution and the mixture. So solution becomes when we mix two things and they mix homogeneously, and when it doesn't mix homogeneously, then it is called as mixture. Okay, so like if you are adding some extra component like salt in the water, then it mixes and it basically forms a solution. That means it mixes very homogeneously, right? Similarly, water and the sugar, that also mixes. But have you ever thought, like suppose you take a glass of water and keep on adding this sugar, so there will be at some point of time where the solubility of sugar will be reached, and the extra sugar which you will add, that will be just in the form of sugar itself, sugar crystal. So that line is this. Okay, so here this diagram is also a phase diagram, but the thing is that here we are assuming that the pressure is 1 atm and we are plotting the phase diagram in terms of temperature and the composition. Okay, so and this is basically one form of binary phase diagram. Okay, binary phase diagram, because two component is there, one is the water and second is the sugar. In the previous one we had only water, right? So that's why whenever you take one component, then you have to add pressure and temperature, but when you take two component, then it will be temperature and the composition. Okay, so see here the solubility at suppose 20 degrees centigrade, it is somewhat something like this. So suppose it is 60 and 70, so 62, suppose I take 62 8%, means out of 100 gram 62 gram will be the sugar which will be in solid form. Now suppose someone adds 70 grams, so the 62 will be soluble and the rest will be in the form of solid. Okay, so at different temperature, if you are increasing the temperature, so what is happening, the solubility limit it is increasing. Okay, so why it increases? As we increase the temperature, the bonds stretch, the gaps between the atoms increases, and the solubility of some extra particle if we add from outside, so that will hold, that has the tendency to hold it, right? Okay, so this thing we have discussed. Means what is the effect of temperature. Okay, now what are the component and the phases? So component, like you take the example of water and sugar, so these two are the components. And what are the phases? Phases are those which are basically physically distinct, chemically same, right? Chemically same it will be. Okay, so basically what is phase? So phase is a physically and chemically distinct material region. And one more thing you can say, which we can separate, like suppose if we want to separate this, then I can physically remove this portion from the material. Suppose I have some tool, so like that. So it is basically physically and chemically distinct material region. So we have the same region, but between we have the same material, and if you go down, then what happens? There are some locations which will be rich in some A element, other location which will be rich in B element. Okay, so that creates a phase. So this is the example of aluminum copper alloy. So we are able to see this alpha phase and this beta phase. Okay, so there are two phases, it has been named. Okay, similarly, how can you understand in terms of atoms? See, this gray color or nickel atom, and this orange color is the copper atom. Now we have added the copper, right? Now we have added the copper, that means the copper will try to get the solid solution over there, but it can happen that in some portion less amount of this copper atom is there, but here you can see that this copper atom is very high, because one layer is the copper, then the nickel, then the copper, then the nickel, then the copper. So in this region the copper percentage is more. So these two will be different, it will look different, right? So that's why we can name this portion as phase A, then phase B, and this all regions are similar to this phase A, right? So we have two phases, phase A and phase B. So that's what it has. If you see here over here, so you can relate this. This is one phase where maybe the composition difference is there, and here the composition difference when it will be, right? So it has tried to explain. Now the criteria for solid solubility, like suppose I am adding something, so this part we have discussed. So for this solid solution, if you remember the Hume-Rodri rule, uh, Hume-Rodri rule, then basically the two elements which we want them to make a solid solution should have the same kind of crystal structure, like nickel and copper. If you see, they both have this FCC and FCC, so it has the tendency. If they also have the same kind of electronegativity, then also it is soluble. And if the atomic radius difference is less than 15%, so here you can see that these are very close, so that will be definitely less than 15%. Okay, so these two have very high solubility in each other. Okay, now next case we will continue the phase diagram. So this phase diagram here, it is given for the two component. Okay, and this particular form of phase diagram is basically called as isomorphous phase diagram. Okay, so why it is called as isomorphous is that the two components are soluble in the liquid state and the two components are soluble in the solid state, but in between the solid and the liquid there is some differences. So that's what here the diagram is there. This is the temperature, this is the composition. Now while drawing the phase diagram, so there are two components, right? So like A and B. Now suppose I mark the composition of only B, like suppose I tell 60% of B, then it is easily understood that the rest it will be A, right? Because it is a binary phase diagram. So it's not necessary to mark both this B and A. If you mark any one, like atom B, because it is made up of A and B atom, right? So and if B is like 60%, then what is the remaining? So that will be A, right? And see here, these two lines are there, and above this line the whole thing is in the liquid, means at this temperature and whatever the composition may be, in this complete region it is liquid. Okay, now if we decrease the temperature and reach up to this location, then we will see that this is the region where we are getting the solid. And if we are in between, like suppose this temperature, this composition, then it will be liquid plus alpha, right? So this is basically a case of isomorphous phase diagram. Okay, so we have two phases in between this liquid and this alpha. Okay, so this is called a isomorphous binary phase diagram. Same thing it is written, so if you read it, then you will also understand better. So these are some different composition it is given, A and B. So a different composition, like suppose you take for A, it is like 1100 degrees centigrade. So this is 68% and 68% nickel. So we have this alpha phase, right? So this is what phase? This is alpha phase, right? Suppose someone asks you what is the phase over here, and this will be your alpha phase. What is the phase over this point? This will be L plus alpha. What is the phase over here? This is liquid. Okay, and now suppose someone asks you on the line, what is the phase? So it is the boundary between this L plus alpha and this alpha. Okay, okay. Now determination of phase composition. Okay, so phase composition, like see here it is given. Like suppose this is the point here, the point A. The 3 points are given, A, B and D, right? See, so A point, if someone asks you what is the composition of this phase, so this is, we have the liquid, right? So Ta, it is only liquid. So what will be the composition of that liquid? So it will be 35 weight percent nickel. So Cl equal to C naught, that is 35%, 35 weight percent. Now at Td, this is D, this is single phase, right? So this is solid. So this will be C alpha equal to C naught, that is 35 degrees, 35%, right? At 1250, this is point B, right? Now this is the critical one. See, this is the point B. Now this is the composition of the alloy, but this alloy contains this liquid and alpha both. So it will be difficult to say what is the composition of this liquid and alpha which is present. So to do that, we draw a horizontal line like this, and since this line is touching towards this liquid, okay, this line is touching towards the liquid, so it will give us the liquid composition, and this line is touching towards the solid, so this will give us the solid composition. So we will have something like Cl is equal to like 32 weight percent approximately, and Cs, that is C alpha, here it will be like 43 weight percent, something like this. Okay, so let's see what is given over here. So this is the tie line, so it is around 32, right? And this, okay, so 32 and that was 43, like that. Okay. And there is one more thing, how to find the phase fraction. Now we have told that suppose you take this case, so it will be something like this. Suppose this is the liquid, sorry, it will be like, we have the liquid, right? We have the liquid, and in between the liquid we have this regions like alpha, the solid regions. This will be alpha and this will be nickel. So we are able to say that in alpha the composition of nickel is this 43 weight percent, and in this liquid the composition of nickel is 32 weight percent. But we are not saying here what is the phase fraction. Phase fraction means how much weight of this alpha is being occupied in this complete system. So that is told through this lever rule. Okay, so to understand this lever rule, so I'll just tell you, like this was your phase diagram, right? So what you take, the point whatever is there, and draw a horizontal line, and this is liquid, this is your alpha, and this is liquid plus alpha, right? This is your point, right? So this is the composition, initial composition of this alloy, that is C naught, and this will be the composition of liquid in this, that is Cl, and this will be the composition of alpha, that is C alpha, right? Okay, so in the left hand side, always while writing the phase, suppose this is your liquid and whatever the next region is there, so first part it will be liquid, right? Okay, so this will be liquid plus alpha. So liquid, it is in the left hand side, right, for this tie line. So this is your tie line, this is called as tie line. So in the left we have this liquid, and then in the right we have the alpha. So to calculate the weight percentage of liquid, so liquid is in the left side, so we will take the values like this. So this is ABC. So we have to calculate for the left hand side. So that means we will take the value of this right hand side, that is BC divided by AC into 100. And suppose I need to weight percent calculate of alpha. So alpha is in the right hand side. So we'll take the left hand side tie length, that is the AB divided by this AC into 100. Okay. So this is the mechanism to solve it. So there is a derivation for this also, but I think you don't need to go to the derivation. You simply learn it. Okay. Okay. So here it is shown this WL. So for the liquid fraction, liquid is it is in the left hand side. So see, we will take for the right hand side, that is S, this capital S divided by this total length R plus S, right? So that will give us the fraction of the liquid. Okay. And if you multiply by 100, then it will be in percentage. If you don't multiply, then it will be a fraction. So S is how much? This is 43 minus this 35. So 43 minus 35, and this R plus S, that means this distance will be equal to this 43 minus this 32. So that's what it has done. So it is 0.73. Now liquid proportion is 0.73, that means the alpha proportion will be 1 minus 0.73. From that also you can calculate, but if you calculate by just the formula, so alpha, it is in the right hand side, this is alpha. So we'll take the left hand side tie line, so it will be R divided by R plus S. So R will be this 35 minus 32, right? So 35, this is equal to 35 minus 32 divided by this complete length. So this will be 43 minus this 32. From there you can calculate. Well, the same thing here it is shown. Okay. So this is just to show the derivation or the understanding. Okay. So like we do the balance of force. So this is like, suppose we have some mass into this length. So mass into length equal to this mass into this length, right? So from there we are getting these things. Okay. Okay. In this we have understood that in this region we have the liquid. Here we have the liquid and the solid. In this region we have only the solid, right? Now when we are cooling it, so what will be the changes that will be visible? Now see, at point A, this is complete liquid, right? So that is shown in a green, this dark green. As it reaches this point B, this alpha will start forming inside of this liquid. So these are small dot are the alpha, right? And this alpha which will be formed here, so that will have the composition this 46%, because I will draw a tie line, right? So this alpha means the composition of nickel in the alpha. I meant to say the composition of nickel, the composition of alpha will be 46 weight percent nickel, right? Now if you cool it further, this C, then again we will make a tie line, right? So once we make the tie line, so the composition of alpha that is again forming will be of lesser nickel content, and the liquid composition will also decrease. That means the amount of nickel in that will decrease. Again, if you reach this D, then the liquid which is present will have this 24 weight percent nickel, and the solid it will be of 36 weight percent. Okay. And E, it will be complete solid of this alpha, that will be of 36 weight percent. Okay. Okay, but see here, but are you able to think here one thing? This is the structure. Okay, fine. Now initially when this alpha it formed, so it was of 46 weight percent nickel, right? So in the, suppose this is your alpha, I am just exaggerating it. So this is the point here, so this will be green point, so that will have 46 weight percent, right? And after this point C, so it has decreased to this 43, so the next layer it will be, so that will contain less nickel, right? Then again the solidification will proceed, so next circle will be again of lesser composition, and then lesser composition. So there will be gradual difference in the composition of the solidification. That means the alpha which will be there, so that will be having some gradient, right? This will be nickel rich and this will be less nickel rich, right? So that's what here it is trying to show. This is the liquid, then alpha we are forming. So alpha it is 46, but as we cool it down further, so you can see the coring effect is there. So this is basically called as coring effect. That means at the core the alpha composition is 46, here it is shown, and just periphery it is 40%, then it is periphery 35%. If you go again, okay, so then 35, then 31 we have, and similarly for the liquid it is also decreasing, and the alpha we are here, okay. So that's what it wants to say, okay. And here it has drawn this basically line to show that since the cooling happens uh, at a faster rate, so for this movement of atom it is slightly restricted, so that also restrict the homogenization of this element, okay. Because this phase diagram which we draw, that is assume that this is a equilibrium phase diagram. That means the cooling whatever happens, that is a very slow rate, okay. So this is, you can see code versus equilibrium structure, so it will try to show you. So this is the coring, right? So if you have the slow rate of equilibrium cooling, slow rate of cooling, then we will not have the coring effect, means this complete material will be of same composition. But if you have the faster rate of cooling, so that means we are not allowing the atoms to move, okay, atoms to move before it is reaching the room temperature. So in the center we'll have the higher composition than the outer, right? Okay, so I think till now we have discussed this. So after this we will discuss the next part, okay. So thank you.